Hello, everyone, and welcome to APS webinars. The title of today's webinar is Teaching Technical Feasibility with Introductory Physics, the Hyperloop module. I'm Crystal Bailey, and I'll be your host for today's broadcast. Thank you all so much for joining us. APS webinars are brought to you as a service of the American Physical Society, connecting you with the expertise of individuals who can offer insight into physics careers, educational programs, and professional development for students, working physicists, and educators. Today's presentation features Randy Jones. Randy will introduce an introductory physics module centered on Elon Musk's Hyperloop concept, which allows students to explore technical feasibility, human desirability, and financial viability using a newly acquired understanding of physics principles. After Randy finishes the presentation, the remainder of the program will belong to you for our question and answer session. Because of the number of people attending this webinar, we are only accepting text questions. So if you would like to ask a question, please type it into the questions panel located on the right side of your screen. You may submit questions through the questions panel at any time during the webinar, and we will answer all of your questions during the Q&A period at the end. We'll do our best to cover everything that you submit, but we also apologize if we're unable to cover everything. Finally, a link to the recording of today's presentation will be emailed to you after the event and will be made available on the webinar homepage. Please allow 24 hours for video upload. We also encourage you to complete a survey, a short survey upon exiting, so that APS webinars can improve its ability to provide you with these valuable services. And so with that, let's get started. Randy Jones is an associate professor of physics at Loyola University, Maryland. Randy received his PhD in theoretical condensed matter from Cornell University and worked as a postdoc on the Quantum Theory Project at the University of Florida. Randy has been a faculty member at Loyola since 1985, where he has taught many advanced computational and design courses for physics and other STEM majors. Randy's current research interests include the development of methods for computational condensed matter physics and computational chemistry. Randy is also a co-PI on the APS PIPELINE project, an NSF-funded effort to develop approaches to teaching innovation and entrepreneurship within physics.
All right, thank you, Crystal, and hello, everybody. I really appreciate you being here. I know this is a pretty busy time of year for most of us, so let's go ahead and get started. I want to get us started. There we go. This idea of innovation and entrepreneurship is sort of big buzzwords around campuses these days, and often it's the case that this stuff is housed in engineering or in computer science and not so much within the physics community. And in particular, students, we find, who may be interested in these kinds of things don't really think of their physics training as being a viable sort of way to sort of, access that kind of stuff. And the whole idea of the pipeline is that we're trying to get people, students, but also the rest of the community to recognize that physicists are really sort of, superbly trained for addressing these kinds of issues. Now, if you're going to try to sort of bring something like this into a curriculum, that can be a pretty major sort of effort. There's sort of project-based learning that's very sort of amenable to that kind of stuff, but it often requires a complete overhaul of a curriculum. And our thinking is that there should be some really simple kinds of things that we can do that could bring these ideas to students and do that at an early stage. So we are looking at innovation entrepreneurship for physicists, and then we're really focusing on what you can do in the first year of physics to get students thinking about the fact that they can be applying their ideas of physics to some of these sort of ideas. Mostly that means looking at technical viability kinds of issues, and that's kind of where we have been focusing, is to get students to recognize that even in their first year of physics, they've got some skills, some knowledge that can allow them to address interesting questions. So the first set of sort of activities or assignments that we came up with are based on the Hyperloop. And most of you and most students are familiar with this. It's certainly Elon Musk sort of does his bill to the public, so most people know about this stuff. There's also just a huge amount of things available out there that are pretty impressive because, of course, he spends a fair amount of time doing the work to sort of get these things out to the public. So let me see, I'm going to just show you one particular video here. This is sort of a technology experiment here, so I'm hoping it's going to work, but I'm going to go ahead and put this up and we'll see how it goes.
It's called the Hyperloop. It's a system of giant suspended tubes. Riding within are capsules carrying people or freight travelling on cushions of air at speeds of up to 1,200 k's per hour, or roughly 1 kilometre every 3 seconds. Hyperloop has been pitched as an alternative to high-speed rail to link cities less than 1,500 k's apart. Musk says it's safer, immune to weather, and 10 times cheaper than high-speed rail. High-speed rail link between Sydney and Melbourne since the early 80s. Their biggest issue, the $100 billion plus price tag. Will someone pick it up and make the Hyperloop a reality?
Okay, so I hope I'm back. So that's just one example. Let me just play you another quick example again, just to sort of point out the things that that could be done here. Well, maybe I will, maybe I won't. I think I can get here, but maybe not. Okay, let's go on. So how do we use this? We can really start in the very first week to address questions that students can sort of think about of this Hyperloop. Now, certainly the Hyperloop, it's pods that travel on magnetic levitation, and most students will think, well, I don't have any information to be able to address that complicated kind of a question, but there are really very simple kinds of things that they can do. So, for example, the first question is just a constant speed sort of question. If you're going to go from Boston to Washington, D.C. at this speed that these things can travel at 760 miles an hour, how long is that going to take? So we give that to students and sort of have them work through that. I don't think I need to work through that for the audience here, but just to remind, it's a good opportunity to get students to practice a little bit with their unit conversion sorts of work. And when we did this activity, about half the students didn't do the unit conversion right, so they got all sorts of sort of strange answers. I should say, by the way, that we've mostly worked with this by, we've got a one activity period a week where students are working in groups and doing problems, and so they do that, and I walk around to sort of see how people are doing. And then the following day, sort of in what we call the lecture period, I often will sort of review the work that they've done and bring up other kinds of ideas. So that's the method that we are using for presenting these ideas. So then you sort of go through the calculation, as I say, pretty straightforward, and it turns out 30.9 minutes. And students who are on the East Coast certainly appreciate that's a pretty amazingly short time to get all the way from Boston down to Washington, D.C. So they're pretty impressed just by that sort of initial sort of calculation. So yeah, so there it is, the 30.9 minutes. And then we sort of get them thinking a little bit about, all right, well, but is that the whole story? Because of course you need to start from rest and speed up, and then you need to slow down to get to the end of the trip. And so the question then is, how much added time does that contribute? And at this point, they don't know about the ideas of acceleration, or at least we haven't addressed it in class, but it's sort of a motivator to say, well, look, we can now begin to address this question, and we'll do this next week in talking about acceleration. So I like to sort of bring things in that will then motivate students for the next topic. So acceleration. So then week 2, when they come in, there's an extended version of this problem then to say, all right, let's find out how much time it takes to be speeding up and slowing down. Now, the way I've presented this here, and there's some flexibility based on how much time you want to sort of use up in doing these kinds of things. The way, if you're reading the wording here, I say, assuming a comfortable acceleration, how much time would this add to the trip? So that leads to the question, what's a comfortable acceleration? And I think it's important that we give students problems that don't necessarily include all the numbers. So I like to do this and ask them, well, what is a comfortable acceleration in this kind of a case? And they're kind of at a loss as to what to do. And so I remind them, well, you can always go Google it, or you can do some sort of a calculation, or you can look up sort of jet plane takeoff accelerations, lots of different ways to do this. And I send students off to sort of explore that a little bit. And then we came up with a value that's 1.5 meters per second squared. And you certainly can, withstand higher accelerations than that, but that's about what the acceleration of a jet airplane on a runway is. And it's going to turn out you're accelerating for quite a while. So you'd be a little uncomfortable if you were accelerating much higher level than that. So another way of setting up the problem, if you don't want to devote the time, is just to word the problem originally as 1.5 meters per second squared and set them to work doing that. That calculation is actually kind of involved. I mean, I've sort of done it here in gory detail, but basically you can calculate the time it takes to reach, let me see if my little cute thing here is working, the time it takes to reach the maximum speed, how far you go during that acceleration phase, and then you calculate how much time you're going to spend slowing down as well. The total time turns out to be 34.8 minutes, which means you add, let me see if I can, 3.9 minutes to the total trip. Okay, so that's a reasonable problem for constant acceleration kind of calculations for students. It takes them a little while to go through and do that. So it's a good exercise, but it's a fairly typical kind of problem that they would address in end of chapter kind of problem, with the advantage here that they are hopefully interested because it's a question about, this Hyperloop. So 3.9 minutes added to the travel time, speeding up and slowing down. But then the next piece that I'd like to do is to talk to them about a graphical solution to this problem. We always introduce sort of using graphical methods, and students kind of think we're just torturing them with it, that, this other way, this other approach. But here, for example, you can really do a nice piece of work with the graphical analysis. Certainly, constant velocity, it's just the area under that curve, which people can understand pretty easily. If you are going through an acceleration phase, then we've got a place where a region where we are picking up speed. And so basically what that means is that that little piece of the area is no longer sort of in the curve. But with the magic of PowerPoint animation, you can see that if you just slide that over with the same amount of area, you can go up to maximum speed and travel and then go back down to zero. And that allows you to see sort of immediately, actually, that the added time is just that T1 on the right-hand side, or the additional time that you have to go through is just the Vmax divided by A. So you can get rid of all of that complicated calculation on the previous page and just do this graphically. So it's pretty rare to find graphical problems that actually make life easier for students, and they generally appreciate that. But by the way, if I just go back to this page, the calculations that I done there with for that initial time was 3.78, and the time that I had come up with at the end was 3.9. This was actually student work. So those two things aren't the same, and that's actually a round-off kind of a problem, which is nice to sort of remind students that they have to be a little careful about round-off. It's also an opportunity to sort of point out that working with symbols could actually make their life easier. I try to do that throughout the semester. This is not an ideal example. Here's the same problem worked out just with symbols. And it's a little ugly, but the nice thing is that when you're all done, you end up with sort of that result that you can get without having to go through the numerical stuff. So it's probably not the best example of the advantages of keeping things in terms of symbols rather than numbers. But as I say, I like to do that, and I point it out to them anyway that that's the case. Okay, so we now have that there's this extra 3.78 minutes added to the travel time. But then the next question that I pose is, if you're going to make some stops, that's going to add that speeding up and slowing down time. And then I also said, suppose you're going to stop for 5 minutes, which seems pretty reasonable at each station. How much time does that add? And I'll zip through the calculation here, but turns out to be 35 minutes to make those 4 stops. And so, in fact, the time that's required to do this trip is now doubled because of the speeding up, the slowing down, and the stops. And so graphically, you can do it like this too. I didn't put in the breaks for the stops there because I got lazy with my PowerPoint, but you could do that. So we add this 35 minutes to the time. So then the question is, does that make the whole sort of process less attractive? And so again, this is this sort of feasibility question that a first-year physics student in the second week has now been able to address. Does that mean that it's going to be less practical to try to do this? And as I said here, it's an issue of human desirability. That's one of the aspects of innovation and entrepreneurship. You can make some high-tech fancy thing, but is it actually going to be something people want to use? So then what I do here is take a little break and ask students to think about what they could do in terms of solving this problem. In particular, is there a way to get travelers on and off the train without it slowing down? So we'll spend some time, students will sort of work in groups to sort of think about various solutions to that kind of a problem. And then I show them, here's one example that has been sort of proposed. And again, these are sort of fancy videos you can watch. So I'll bring that up and hope it works. I can narrate a little bit. There's the train coming by, and it's got a little sidecar that circles around and joins it as it comes into sort of the town. So there it is. The quality of videos and stuff is just great. So now you've transferred passengers and everybody's happy. The little assistant car slows down and heads back to the station while the train goes off at its constant speed without having to slow down. So we talk about that, and then I ask students, well, does this add some extra complications? Is this really a good solution? And it's not hard to sort of think about things that are going to be a problem with that. Remember that it takes 38.6 kilometers to get up to speed. So that means that that little assistant car has to travel 38.6 kilometers before it can join up with the original moving train. And then the question is, how much time and distance does it take to transfer passengers? Because this thing is moving at this high speed. That's added distance that they have to travel along together. So we're looking at some pretty significant large distances. And then, now what happens if people aren't all the way from one car into the next? When they reach the point where those tracks separate, there's no choice but to pull those things apart. And you can imagine what happens if you're halfway between the two cars when they have to get to the point of separating. So there's a number of issues with that idea. One other one is the fact that train, that's the sort of assistant train, has to go through a circular path. And I ask the students at this point, so is that a problem? Is there an issue with going around in a circle? And it allows me to sort of lead into the idea of centripetal acceleration. And again, I can talk about sort of the fictitious force, although that's getting ahead of myself as well, of linear acceleration, and then the fictitious force of going around in a circle. Can make this suggestion because I thought it was a pretty good one. So the idea is to have a detachable car. Now, when the train comes in, the car is sitting at the station, but it begins to accelerate forward and is moving at the speed of the train as it approaches. And you may have noticed there that the last car on the train separated and then it slowed down at the same time. And that could all happen on a single track. It could all happen with some sort of single set of cars. But then I remind them, well, what are the additional complications that adds? And there are a couple of things. You have to worry a little bit about possibility of collisions here, and that gets us into a topic for the next month. But then also you have to recognize that people who are in that lead car, if they want to get out at the next station, they have to work their way all the way to the back. Of course, there isn't a whole lot of time to make these things happen. So there are sort of aspects of that they have to sort of think about as well. But again, we've got students who are coming up with creative ideas. They're using their innovation and entrepreneurship, plus their really basic level of introductory physics to be able to address some of these questions. Well, then, as I said, I had brought up already the idea of centripetal acceleration. And the way I sort of address this is to just show them the map of going from Boston down to Washington and say, well, if you want to make some stops at various cities along the way, you can't just do that in a straight line because they're not laid out that way. So you have to do some sort of a circular curved path. And I have students work with compasses and pens and whatnot and sort of lay out what is a possible path for this train to go from those two spots, stopping at different stations. And of course, there's some arbitrariness here, but it gets an idea across. And in fact, they can then measure the radius of curvature. There's a little bit of unit conversion associated with converting centimeters on the map over to distance. When they calculate the centripetal acceleration, it turns out to be about 1 meter per second squared. So that seems like it isn't an issue, although, well, two things than that have to be dealt with depending on sort of the terrain, because you'll notice this thing's going through the ocean at a couple points here. So, that's a pretty crude approximation. And the other issue, of course, is that acceleration is added to the initial linear acceleration when it's picking up speed. And so that gives me an opportunity to talk about tangential and centripetal acceleration and the combination of those two. I also talk about fictitious forces a little bit. So again, it leads into things that sort of are coming up later in the semester. So then additional Hyperloop examples. I decided not to sort of work through any more of these, although on the Pipeline website, the document is there that has all of these various examples worked out. So as I said, the tangential and centripetal acceleration is there. And then air resistance, certainly you can talk about that. This thing travels in an evacuated tube, but that's why it's able to do that. You can talk about work and energy in those aspects also. I mentioned bringing up ideas of collisions if we use that idea that my students have. We did a little section on relativity, so I had students calculate how much younger a passenger would be if they went from Boston to Washington. And it turns out to be pretty minuscule, but that helps people put some things in perspective. And in the same way, on the last homework assignment, I had them calculate the speed of the space station, and I somewhat jokingly just said, compare that to the speed of the Hyperloop. And the students actually were pretty into it. It turns out the Hyperloop is significantly slower than the speed of the space station. But again, it helps them get a little bit of sense of the various magnitudes of these things. So then, there are really multiple kind of opportunities. And the way we sort of approach this is to look at each topic in physics and say, is there an opportunity to use this in some fashion in the Hyperloop? And we are hoping that we're going to get people to volunteer ideas for this as well. So we're on the website, we've got a place and we've got some opportunity to sort of contribute your own ideas as you come up with various things. There's an entire second semester of general physics that is open to this kind of thinking as well. So I want to talk a little bit about some other examples as well as the Hyperloop, because there's nothing particularly magical about that. If you just spend a little time in the New York Times science section, you can often find things that have sort of relevant questions to address, even at that sort of general physics level. So the way I present this to students is the $1,000 question. And if you've seen Shark Tank or some of these other shows, it's that sort of idea. Would you invest $1,000? I sometimes have to change that to $100 for my students to have some sense in my company to buy or sell various things. And so, for instance, one of the examples is this thing that is actually produced. It's called an all-terrain wheelchair. And the idea is that it's got these levers on it to allow you to get a greater amount of torque, to apply a greater amount of torque. And I put a problem together for this as well. It's a great example of getting students to think about how torque is generated and the various aspects of that. So that is actually something that is produced. Can ask them about, solar panels on a car. And again, this is a little ahead of ourselves because we don't really get to electrical and light sort of phenomena till second semester. But again, I use that as sort of a prod to sort of tell them that they'll be able to address these kinds of questions as they're moving into second semester. Turns out you can't really get enough solar power out of that little panel to do very much in terms of driving a car. But again, something left for the next semester. Then I'm constantly reminding students that the first question in these sorts of things is the feasibility. Does it make sense at all to try to design a car with this solar panel on top? And so the feasibility would be, let's just calculate roughly how much energy we could generate from that, and is it going to be worthwhile? And then I remind them that it's their physics training that makes them the experts. And if somebody came to them with some idea, the first thing that they could do is do a quick and dirty calculation to see whether it's completely out of the realm of the possibilities. So then I also sort of talk about this sort of, would you invest your money, and talk about other things that are a little further out there. Pyramid power, for instance. It's pretty amazing. You can actually go to the web and find the people who are selling little pyramids that are supposed to make you think clearer and sleep better and keep vitamins more potent for a longer period of time. And it's pretty clear, thousands of dollars, and actually made money on these things. So it's not something necessarily to be proud of, but it can happen. And then other things as well, magnet therapy, I sort of talk about that and point out that, well, at least there's things you can actually sort of go and address and experiments you can perform to see if magnets are actually accomplishing something. I think it's pretty clear they're not, but I leave it to students to sort of recognize that they can go and address these kinds of issues on their own. So then I sort of turn students loose to be thinking about what other ideas might they have and be thinking about. So I was gonna, Crystal, are you able to tell me about how much time I have? Are you there?
Yes, Randy, you have a few minutes. I'd say maybe 5 more minutes.
Okay, well, Let me go on then. I'll talk fairly quickly about something that's a little different. And it's an approach that's a little different, where I sort of talk about some physics, and then I ask students to think about what they could use that physics for. And so I talk about gravitational potential energy in climbing a set of stairs. I'll go through this somewhat quickly, so it'll be on the PowerPoint that you're able to access after the end of this thing. So clearly, mt times delta y is going to be the change in gravitational potential energy. And again, I ask students to come up with these numbers, and it causes them a little bit of consternation that I haven't actually given them a number, but they can sort of make some sort of approximation. Height of a flight of stairs, you'd be amazed at how much terror that generates, but I have them look it up, and we come up with about 4 meters is the height. So the gravitational potential energy is 3,000 joules, and then I sort of turn that around a little bit. This is getting at some actually deep philosophical questions. How much work do you do when you climb a set of stairs? It's got to be the same amount. That's your change in gravitational potential energy. You actually do that work on yourself, which is a little bit interesting, but they don't worry too much about that. So now I ask, okay, what's your power output as you leisurely climb a set of stairs? And here, my wording isn't exactly right. I'm trying to get at, if you're going to climb a set of stairs for a long period of time, how much power output could you generate? And so clearly the formula is the work divided by the time. How long does it take to leisurely climb a set of steps? I tell them, go do it. And in fact, I send them out of the room to go. We have 4 flights of stairs to go from the basement up to the 4th floor, and time how long it takes. A bunch of eager go-getters, and they claim they can do it in about 15 seconds, which is probably a tad optimistic. But if you do that, then it turns out you're generating about 200 watts of power while you're climbing those stairs. So yeah, I think 100 is probably more like it. But anyway, that's what we use. Then I point out, okay, if they're on a stair climbing machine, is the work you do the same? And that's interesting, but pretty clear it has to be the same amount of work. You're basically doing exactly the same thing, force on the bottoms of your feet, covering a certain distance. Where's the energy go? We kind of know it goes to thermal energy for, heating up the room. But then I asked them, okay, can you think of ways that you could use this idea that you are putting 200 watts of energy power into this stair climber? What could you use that for? And so I give them some and they want to use it to charge their cell phones or run their stereo or their, TV or something. But then okay, so there it is. And again, I talk about doing that next semester. If you see this, when you get the PowerPoint, you can go click on this. One of our students in an upper level class designed a bicycle that would generate electric power, so it's kind of fun. But then what I do is I go talk about something really completely different in a sense, and go and talk about sub-Saharan Africa. And again, I'll be pretty quick about this, but it turns out that agriculture and lack of irrigation is a serious problem in these regions. And so the question is, could we develop, that I give to students, could we develop a human-powered pump for irrigation? And in order for them to sort of address that question, again, they're in a panic. Well, would you invest $1,000? Feasibility, then what do you need to know? Well, lots of things, right? How much land, how much water, how far do you lift it? All things that are unknown, but I send them out to sort of go explore and find all these things by looking them up in Google. And so come up with various numbers, an acre. Water, we came up with one estimate as 20,000. Of course, that can vary a lot depending on climate and whatnot, but that's just an approximation. Again, it's good to get students comfortable with not having exact numbers. We decided 10 meters seemed reasonable. Seems reasonable. So then I'll skip through this. You could do the calculation pretty quickly. 2.8 hours with those various numbers. So seems reasonable. Would you invest $1,000? So certainly we talk a little bit then about, well, there are other issues you have to address. You've got the pump design, what are the materials, and how much does it cost? So these are all part of the innovation and entrepreneurship sort of questions. I said here, by the way, that maybe you do need to bring an engineer on board for some of these questions. But this is sort of an opportunity to say, look, all these other questions about feasibility, engineers aren't really trained to do that. They're trained to build something. So when you actually decide it's worthwhile and you want to build it, then you can bring in your engineer. So after having sort of addressed this, then what I do is I go and talk about this company called Kickstart that actually has built these things and designed them and made them work, and is both supplying an incredibly important need in sub-Saharan Africa and actually making a reasonable sort of profit at the same time. So there's a YouTube that I will not show you here video that sort of talks about how they put this together and the difference they're making in sub-Saharan Africa. And really, when I show this to students, there isn't a dry eye in the house. So I encourage you to go watch it. But basically, they've designed a pump, and here it is. It looks pretty much exactly like you would expect. And they're able to do basically exactly what we had talked about. And they're able to use that to irrigate their fields, and it's making a huge difference in the lives of many people there in sub-Saharan Africa. And Martin Fisher has won all sorts of awards for this work that he's done. So again, that's another way of sort of introducing students to this idea, to sort of give them the ideas, and then, yes, okay, this one has been done already, but there are other ideas that are out there that are waiting for you. Now, I'm just about done, Crystal. So I just want to point out, we also have a senior level course. Our idea is to get students interested in these ideas, and we sort of build through it for the 4 years while they're physics majors. And then there's an upper level course that specifically deals with a lot of these other issues about innovation and entrepreneurship and how you put together, say, a business plan and whatnot. And it's a successful course. It's both physics, computer science, and engineering, so it brings people together from all different disciplines. Let me just say that one of our goals here in doing this work in the first year is that we have engineers and physics and computer science people primarily in that first year course. And as I said, a lot of people are thinking they want to be engineers because that's the way to get to all of these ideas of the innovation and entrepreneurship. Our goal here is to convince some people that physics is a viable, if not better, sort of approach to be able to go through and sort of take these ideas and be able to sort of be successful with them. So we are continuing work. We're going to do some work to try to assess how things are working. But one of our goals is to be able to, convince some people who are thinking engineering that, well, maybe there are other possibilities and physics could be one of them. So that's a summary page then of the Pipeline website. It's got the link there where you can go. It also has, I'm not sure if it'll have this link up there, probably will, and then it's got the documents that are the problems that I've sort of gone through, and some of the ones that I've hinted at too are up there as well. I think I'm done.
Okay, well, thank you so much, Randy, for this great presentation. I think this is just such a neat thing that y'all have done, and as I've said before, it's teaching what I think is a vital, essential quality of being a physicist, which is the confidence that you can make good, educated, well-informed guesses. A lot of people kind of encounter this stuff that you've done and think, oh, that's engineering, and it's absolutely not. I think it's very distinct, and I think it's just marvelous. So one of the questions that we've gotten, and I'll just answer this for everybody, is whether the webinar will be available. And yes, we're recording it, and it's going to be, first of all of you have registered, so you'll get an email from GoToWebinar with a link to the recording. And we are also going to post it on the page where the Hyperloop materials are stored. And I actually sent a link out to the whole audience with that, the Hyperloop materials. This webinar will be embedded there. On YouTube, it'll be able to access the recording of this video. Okay, we've got some other really good questions. Excellent. So can you just say a little bit more, just clarify sort of how much time the Hyperloop module typically would take of class? It seemed like it was over several different periods. Can you just give a general idea of how much time would be needed to go through the module?
Yeah, so we have, as I said, one class period each week. That's an hour and 15 minutes where students are working on problems in groups, and we have a teaching assistant, learning assistant, and myself, me as well, circling and helping students answer questions. And we'll maybe do 4 or 5 typical kind of end of chapter problems in that time period. And one of them will be, not each week, but I try to do something each week on the Hyperloop. So that means sort of 1/5 of the time spent in that period is on the Hyperloop. And then the next day, I'll do a little bit of review of some of the questions that people had, some of the problems that people had issues with, but I'll usually use it as a way of doing some of the issues with the Hyperloop. So maybe 10, 15 minutes there. So what are we talking? It sounds like half an hour, but again, these are pretty much standard end of chapter problems. So it's not really that something else is sort of being replaced. It's really just using these examples. And I have to say that students came into this problem session after the first month, and they were like, is there a Hyperloop problem today? What are you talking about in the Hyperloop? And trying to guess in some cases what the questions were going to be that dealt with the Hyperloop. So that was encouraging to see.
Yeah, that's so cool. I'm not a bit surprised. Okay, so there's some really great questions coming in. So it seems like it's kind of geared, I mean, I could imagine this being taught to physics majors and also adapted to an intra-class where you've got a mix of physics majors and engineering majors. Are there any ways that you would think about adapting this module to address those particular audiences?
You mean individual, if it were physics, all physics people versus all engineering people? Is that what you're getting at?
Mm-hmm. Mm-hmm.
You know, not really, because this is really basic physics and it's an application of physics. And, you know, we all try to find various applications of our physics principles, and textbooks are full of them, and the biology sort of focused textbooks have their biology examples. But, you know, so finding examples that sort of apply the basic physics principles doesn't really matter whether you're doing Hyperloop or whether you're doing the operation of MRI. Well, get a little far afield there, but so I would say no. I'd use this for any group of people learning basic physics.
Related to that, what would you think? I know that in many cases, in engineering as a major, you know, their students have to take introductory physics courses. Do you think that maybe engineering educators might also be interested in these materials because it would be a way for them to learn physics, but seemingly more contextualized in what they're used to as engineers?
Sure. I mean, since these problems are addressing the real basic kind of physics concepts, I think the engineers are sort of moving beyond that, but they might very well want to look at this pump, for instance, the human-powered pump, and have students do some calculations of fluid flow. If it was a fluid dynamics class, for instance, fluid flow through pipes, and add on that next level of either feasibility or design as to how to make something, you know, actually work now that we've demonstrated that it's a feasible concept. So I would imagine they wouldn't necessarily take this directly, but they could very well take the sort of ideas and then build off of those.
Mm-hmm. Mm-hmm. Yeah, absolutely. So you also mentioned that this is kind of a springboard for helping students come up with other ideas for technologies or, you know, different ways they could apply physics. Have your students actually come up with anything interesting in addition to what you've discussed here? And do you have any tips for kind of spawning that ideation in students?
Yeah, well, so in the senior level course, that's really Bahram, my sort of co-conspirator in this work, teaches that course, and he starts off right from the beginning and has the students work in groups and think about problems that they would like to solve, just, you know, completely brainstorming all sorts of things. And some of them are thinking about poverty, and some of them are thinking about keeping the trash out of their room, but they sort of cover the full spectrum. And as he goes through the course, he has them select a particular sort of, you know, winnow that down and select a topic. And then by the end of the course, they're actually building some sort of a project to sort of, you know, try to solve that particular problem. And he's had students come up with all sorts of innovative kinds of things. And since it's engineering, computer science, and physics, some of them have been setting up an emergency call system on people's cell phones to sort of help students if they're in trouble on campus. Another group had a design for how to guide Zamboni machines around an ice skating rink because one of the group members drove Zambonis during his summer breaks, and he recognized that there was a serious difficulty in terms of getting that process to work. Who knew? But it was actually a very innovative idea for taking care of, you know, what he recognized was actually a pretty serious problem for ice rinks. They lose a fair amount of time when they've got the Zambonis not quite matching, not quite meeting the criteria. So, you know, once you get people together and start thinking about what could be done to make the world a better place, it's interesting what they come up with.
Yeah, that is great. And do you have a sense of whether any of these kinds of ideas that have come from students might lead to an actual product, or have any of them pursued that as far as you know? Or?
Yeah, I should have Bahram here, because this group that came up with the idea about how to have an emergency sort of call system has actually brought that to market, I think, and I should know about the Zamboni, because I really hope they made that work, but I don't know for certain. Other projects that I'm trying to think of, I can't remember right now, but certainly, they're ideas that we hope people have been able to sort of follow through with. So yeah, we could do another webinar, and he can talk about his successes there. So.
Right. And as Bahram will often say, Bahram is also a PI on this pipeline grant, and is in the audience. Hi, Bahram. It's not just and I think this is a really common misconception when people encounter what we're doing with innovation and entrepreneurship and physics education. We're not expecting everyone to actually start companies, right? It's about teaching them mindset and helping them understand, first and foremost, that what they're learning about physics makes them very powerful innovators, and it can be applied in a lot of different directions to solve a lot of different problems. We certainly don't expect, all students to become, have their own startup and be successful. That's a, very difficult process, but, empowering, teaching them this entrepreneurial mindset empowers them, and it connects them more deeply with the physics they're learning, which studies can show will improve how they're learning, and will also improve retention of physics majors. So that's why it's really valuable.
Absolutely, and and it only takes one to donate a new science building for us after they've sort of
make their millions like Elon Musk. Yeah. But do you also see in your students any any sense that they are connecting what they're learning with just physics careers, or thinking about different career possibilities?
Yeah, certainly. So up to now, it's been sort of anecdotal, and that's one of our plans, is to start doing something a little more careful about this, to be able to do some careful assessments. But I've had a number of students who have come to me after class and talked about these sorts of ideas. And we've had a number of students who then have signed up for Bahram, Dr. Brugani's senior level class to do that innovation entrepreneurship. So it certainly has generated some interest. And on my student evaluations, I do have comments that people love the Hyperloop questions and whatnot. So it's clear it's at least getting the attention of some number of them. And again, we need to do the assessment a little better to sort of know for certain. Now, it's a little tricky. I know that when I've taught courses that were primarily biology majors and used textbooks that had lots of biology examples, I would get some criticism from students who were not biology majors but were in that course for other reasons, that it was too applied to biology. So you have to be a little cautious. But again, we don't present this as if these people are all going into transportation engineering and so they need to know this. We're presenting it as, here's a really cool thing, this Hyperloop, and let's just see what we can sort of, come up with it. So.
Mm-hmm, mm-hmm. Yep, absolutely. So what is the most challenging aspect of teaching these modules, would you say?
Well, it's a little bit of a change in mindset. You could just present them as end of chapter kind of problems and let it go at that. But what I like to do, what I've said here, is to have points where students have to be thinking outside the book, I like to say, where they are coming up with numbers on their own, the comfortable acceleration, or how much water does it take to irrigate, because students are very uncomfortable with that, and it's because textbooks almost never do that. They'll give you every piece of information that you need. And so I think it's incredibly important because the real world doesn't always give you all the numbers you need. It's incredibly important for students to get somewhat comfortable with that. I think this is a good opportunity to do that. If you try to do it in a standard kind of, problem at the end of the textbook, students feel like you're just abusing them for no reason. Whereas I think here it can help students be more comfortable with it. But it is challenging. Students, are used to doing things the way they've always done them, and when they don't have a particular number, it's it's challenging for them. And that also takes a little bit more time too. So you got to recognize that that's got to be some time that you don't spend in other ways.
Mm-hmm. Yeah, but it's interesting because a lot of times what we've talked about, one of the motivations for sort of pursuing PI, physics, innovation, and entrepreneurship education, is that most of the students that graduate from physics programs are not going to be academics. They're going to go into industry. The vast majority will go into industry careers. And it'll either be in companies they start or in other people's companies. So that mindset is really important. But, another thing that I just remember as an experimentalist grad student myself, there was one particular day in the lab where I was doing an experiment, and I was what the number, how much it weighed. And I was like, oh, the real world, it's not always printed on the bottom, right? So again, having to sort of think about these ways to estimate things and think outside the book, the textbook is really, really important, even if you're destined for a career as a research scientist, even for the very small number of people who are going to be doing academic research careers. These are all still essential skills for physicists, right?
Yeah, that's right. And that is one that sometimes people hear, oh, innovation, entrepreneurship. What about the physics majors who want to become academics? Aren't you leaving them? Aren't you ignoring them or not address? And as you say, it's not that way at all, because these are skills you need in pretty much any endeavor. So.
Mm-hmm. Yep. So are you thinking, is there anything on the horizon of any new modules that you might be coming up with? So on the Pipeline website, we've got the Hyperloop module, we've got the human-powered pump activity, we've got the user innovation module. What other things might be coming out soon, or are you working on anything new?
Yeah. Well, I have written up a problem for that wheelchair to sort of have that analysis, but really what we want to do is move into the spring semester and do the same sort of analysis, sort of what topic in the spring semester, and it's mostly electricity and magnetism, could we be using here to talk about issues with the Hyperloop. But then that gets a little tricky. We're certainly, I don't think, going to be doing magnetic levitation. That's a little bit sort of difficult to do at sort of the first year level, although we could do a little bit with it. But we may be doing other kinds of things as well. That solar powered, solar panel on the top of the car is a good example. Is this a practical kind of thing to do? And it turns out people are actually thinking that if a car is parked all day in the parking lot in Arizona, that they can actually collect up enough energy to power some of the electrical sort of parts of the car, not necessarily to drive it. But anyway, yeah, we're trying to think of new things to do. We're also thinking about the labs that people do in their first year, but also we like to be able to come up with sort of ways to incorporate this thing into upper level classes as well. And the labs are one. Have the labs be a little more, particularly that lab that physics majors do, where they're introduced to all the grand concepts of modern physics and speed of light and the photoelectric effect and all those sorts of things, to see if we can't tie that to something that is a little more current and interesting to students. Because again, a fair number of students say they're majoring in physics because they just want to understand the universe, and that's beautiful and that's wonderful. But there are other students who are going to major in physics for other reasons, and we want to make sure that we don't leave those feeling like there's nothing in physics except the grand unified field theory.
Mm-hmm, absolutely. Yeah, so we also have a question about how, and this will probably be our last question, about how, if there are other faculty who are interested in joining our efforts and collaborating on developing modules. So, I mean, as I already mentioned, this is part of the Pipeline project, and there are 7 institutions that are involved in developing these kinds of approaches. So on the Pipeline website, there's a lot of materials there, but if this is really important, I think at this stage, we really want to develop a community of people who are actively sort of creating these approaches and learning from each other. And one of the ways we do that, we have our Pine newsletter that goes out every month. So if you have not signed up for that, if you go to APS, this URL that's on the screen, go to aps.org/innovation, sign up for Pine News. If you want to submit something to be included in Pine News, please email me, let me know. We're always happy to include stuff going on out in the community. If you have materials that you would want to have maybe shared on the Pipeline website, send it to us. We're very interested. So yeah, we want to be in touch with you. So yeah, get in touch with me. Randy, do you have anything that you would want to add to that, or?
No, just that'd be wonderful. We're always encouraging people to sort of give us ideas that we can sort of work through, but also, work it through yourselves, give it a trial run in your class and see how it goes, and then put things, as you say, we need a community of people who are trying to make this happen. So.
Yeah, absolutely. And I will also say that there are conferences and gatherings that are good opportunities. We have often had a presence at AAPT, American Association for Physics Teachers meetings. I had a few of us there. We always send out that information to the Pine News and, the newsletter. So if you get that and you're going to be at that meeting, let us know. We'll meet up, we'll get lunch or something. There's also an organization called VentureWell, which really does a lot to encourage innovation and entrepreneurship education in STEM. The Pipeline cohort is almost always at their open conference, which happens every March. So that's a really great resource for anybody out there looking to connect with us and a broader community of practitioners. There's a lot of people who've been working on teaching this stuff, not just in engineering and physics, but in business and in the arts. And the open conference is a really cool way to bring people together across disciplines to share what they've learned, so we highly encourage everyone to take advantage of that. So
if I may, Crystal, let me just add that, again, it's easy, I think, to feel a little overwhelmed because you run into people who are sort of promoting a complete rework of, say, a first-year curriculum to do X, Y, or Z, and it can feel like, oh, I'm never going to be able to do this in my department. And our whole sort of philosophy here is that little things can sort of make a huge difference without, if you've got the time and the effort and the support that you want to put in a whole new program of project-based learning or something, that's great. But remember that something, very small can be enough to sort of really get people sort of sitting up and paying attention. So that's my sort of take-home message for the day.
Absolutely, Randy. Yeah, you don't have to not teach a bunch of physics in order to teach this stuff too. I think that's very important. Okay, so that is unfortunately all the time we have. Thank you all for the wonderful questions. This has been a really nice discussion. And again, if we didn't get to your question, we apologize, but you can certainly follow up. You can send an email to webinars@aps.org or to me, bailey@aps.org. Sign up for the Pine News also, and reach out to us. We want to connect with the community. As I already mentioned, both a recording of the video and slides of this presentation will be made available both on the webinar homepage and on this Hyperloop page that's in the Pipeline materials. So, and you'll be getting an email that contains a link to the presentation. It'll take about 24 hours for that to come out. And lastly, as you were leaving, in order to help us continue to develop quality webinar presentations, please take a moment and just complete the short survey as you exit. We'd love to have your feedback. That wraps up today's event, and we hope you'll join us again next time. American Physical Society